Hello folks, this is Ashikul Islam Deep. Today I am going to talk about geodetic motion of massive and massless particles in Levi-Civita spacetime. Levi-Civita spacetime given through this metric tensor is a vacuum solution to Einstein equation which is cylindrically symmetric. The metric tensor possesses two independent parameters sigma and p. Sigma represents the mass density and P represents the angle defect of the spacetime. The metric tensor written in terms of bookkeeper's coordinates t, rho, phi and z. The metric tensor is not asymptotically flat. Also, it can represent the spacetime of a cosmic string. If you take sigma tends to 0 limit, this metric tensor goes to Minkowski metric tensor. If we analyze the motion of a massive particle in this spacetime, we get these integral results for t, phi and z written through the integrations of rho. So these integrations may look really complicated, but they can be used to generate time series data numerically. Also, we can generate approximate trajectory in weak gravitational field using these expressions. Similar analysis we can do for massless particles to give these expressions for t, phi and z in terms of rho. Now, this expression once again can be used to generate time series data. However, for special cases like a equals to 0 or b equals to 0, this expression reduces to Euler-Gauss hypergeometric function. Now we can have a Newtonian parameter for Newtonian interpretation for parameter p, which people have been looking for a while. So from previous papers, we have a relation between sigma, which is the spacetime parameter in Levi-Civita spacetime, and the mu, the linear mass density of an infinitely long straight mass. The relation is mu equals to sigma over 1 minus 2 sigma plus 4 sigma squared. If we calculate the Newtonian gravitational field, meaning the Newtonian gravitational potential basically for this mass density, we get approximately 2 sigma over 1 minus 2 sigma log of rho over r, where r is the point where we have taken potential to be 0. Now, from Einsteinian gravitation, if we take the tt component of the metric tensor, that should approximately represent negative of 1 plus 2 phi, which in turn can be approximated as negative of 1 plus 4 sigma divided by 1 minus 2 sigma log of rho over p. Now, comparing that result with the Newtonian gravitation, we can identify p to be r, which means p has a classical explanation or interpretation that it can be treated as the origin of potential. Now we can look into few massive particle orbits in Levi-Civita spacetime. You can see in the first diagram a single loop orbit which is not precessing. That's why it has a parameter 110. The next one is a little bit precessing, so it has 1 1 then 0.010. The next one has a zoom whirl effect, so it rotates one extra time through the cosmic string. The second one is the corresponding precessing version of the third one. In this diagram, again, we see some more zoom whirl effects. So the first diagram we see, it's again one petal curve, but with 2 extra rotation. The second one is the precession version of the first one. The third graph, however, represents a 2 petal curve which is closed. The second one, the fourth one is basically a precessing version of the third one. Thank you for listening. You can find this paper on archive. Thank you.